So we define some graph concepts. So this part has several definitions in it. Some of them are standard, so bear with me. So directed graph is defined in the usual way. VE, V is a set of nodes, and E is a set of pairs of nodes. So this is a directed graph, and if it is undirected, then every element of E, every edge is a set of two nodes different from each other. Okay, and so if I don't say explicitly undirected graph, then I mean directed graph. Okay, so one type of graphs that we look at are featured graphs. And what are these? These are graphs where every node is associated with a feature vector, a numerical feature vector, like in this figure here. And if we look at the formal definition, it means that we, in addition to V and E, we also have this X that maps every node into a feature vector. And so the usual representation of X in machine learning literature and also in practice is by a matrix. Okay, a matrix of V rows and D columns. And for that, we basically assume that there is some predefined ordering of the node because you need to know what are the features of the first node. This is the first row. So what is the first node? What is the second node? And so on. Notationally, instead of writing X, big X of V, write it as small x with the subscript V. And there are also, usages of the edge features, and we might mention them here and there, but we're not going to focus on edge features in the course. So assume that there are no edge features, but if we need them, then I'll say that explicitly. Okay. Do realize that every node has in a featured graph has the same dimension for its features. And so if the edges are also featured, then there'll also be a fixed dimension there as well. Now, another important concept is a label graph, okay, or a typed graph, which means that every node and every edge is associated with a label. In terms of the definition, we add to V and E this LV, LE, and lambda. LV and LE are the node label, the sets of node labels and edge labels. Lambda maps every node into a node label. And E is defined a little differently. E is now not a collection of pairs, but rather a collection of triples. The source node, V1, the label, the edge label, tau, and the target node, V2. Okay, we might write lambda of E when we want to refer to this label tau. Okay, now an important assumption that we make or restriction that we make is that the edge label determines the labels of the source and the target nodes. Okay, so here, for example, if I say TC, then I implicitly also imply that the source label is take and the target label is CRS. TC maps take to course. Okay, TS maps take to student. Formally, this means that for all edges V1 tau V2 and V1 prime tau prime V2 prime, if the labels are the same, tau equals t prime, then the label of the sources are the same, lambda of v1 equals lambda of v1 prime, and the same for v2. Okay, now when we combine labels and features, we get what we call a heterogeneous graph or a heterograph for short. Okay, and importantly, now nodes that have different types may have features of different dimensions. So formally, what it means is that to the definition of a labeled graph, we also add D and X, okay? And D associates feature dimension with every node label, okay? And now X maps every node V to a feature in which dimension? The dimension of the label of V, okay? Now, an important concept is the idea of type consistency, where two graphs are basically, they have the same structure or meta information. So they are type consistent if they have the same set of node labels and the same set of edge labels. And every edge label is associated with the same input and output or incoming and outgoing node labels in both graphs. And they have the same, dimensions, meaning that for every node label, the dimension of this node label, of the features of nodes with this label in the first graph is the same as in the other graph. Okay? And we can also define it through a schema. So two heterographs are consistent if they have the same schema. How do we define a schema for a heterograph? Very simply, you can see the example here. It will say, okay, we have here the take, the course, and the stud, and we have edges labeled with TC and TS, and the dimensions of the corresponding nodes are mentioned here, 2, 3, and 4. And so this is a schema, and this is a heterograph that corresponds to the schema. Okay, so a heterograph schema is consists of LV, LEM, this new M and delta, and LV is a set of node labels, LE is a set of the edge labels. M maps every edge label to a pair of node labels, source label and target label. And delta gives us basically the D, maps every node label to a dimension, to a natural number. And so a heterograph G um, over this schema, it corresponds to this schema LVLE delta M if you know what we expect, the same set of um, node labels, edge labels. The edge labels are consistent if you have an edge from U to V labeled tau, then m tau is equal to the pair lambda, the label of U, comma, lambda of V. Okay? And then D and delta are the same.